All right, we're a few minutes late, but we might as well get started. In this review session, we're going to go over the practice problems from chapter 29 and 31. And we'll do the chapter 29 problems first. Remember, the thing to focus on is being able to tell reaction types, which is nothing really new. We did something real similar way back in chapter 6. But I've given you a list of reaction types in the practice questions. I may or may not do that on the exam. If I do give you reaction types, they may or may not be identical to this. But the goal is to pick out, in each case, the reaction type. And the way you do that is by noticing the change that takes place in the molecule and being able to categorize it as one of the types of reactions that we went over in chapter 29, which are all really review from the second semester of organic chemistry, maybe some from the first semester. Yeah, I guess hydration and dehydration really come from the first semester. Good, so let's identify what goes on in this first reaction. You'll notice it doesn't matter that we're not given reagents here. You may or may not be given reagents. There's still enough information to figure out what type of reaction there is. And the way you do it is by focusing on the change that takes place in the molecule. And here the change is that we go from a ketone to a secondary alcohol. You're going from C double bond O to C single bond O. And so you have more bonds between carbon and an electronegative element in the starting material than you have in the product. And so that means that this step is a reduction because we have, because of that. You could also say that it's a reduction because there's more bonds to hydrogen in the product than there are in the starting material. The product is an extra bond to hydrogen from the oxygen. And of course, there's also the new CH bond that I didn't draw. So there's an extra CH bond there that wasn't there in the starting material. So you can look at it either way. Fewer bonds between carbon and an electronegative element in the product than in the starting material, or more bonds to hydrogen in the product than in the starting material. Let's move on to the next one. In this case, you have the ketone turning into a secondary alcohol, but you also have a primary alcohol turning into an aldehyde. So you've effectively got a reduction and an oxidation occurring at the same time. And we talked about reactions of this type in chapter 21, I believe, when we first introduced enols. This is an example of a keto-enol tautomerization. And keto-enol tautomerizations are an example of an isomerization. And the way you know that an isomerization has occurred is that both of these molecules have the same formula. It's C3H135, C3H5, O3P, O4P, wait, O5P. They have the same formula. Where we've added a hydrogen onto this carbon, we've taken a hydrogen away from this carbon. So that's how you know you're looking at an isomerization, when the product and the starting material have the same molecular formula. All right. In this next one, a rather dramatic change has taken place in the molecule. We've lost this entire piece over here. And that piece, I think you will agree, is CO2. And we defined what loss of CO2 is. We talked about loss of CO2 in chapter 22 when we talked about, let's see, the acetoacetic ester synthesis and the malonic ester synthesis. That's one of the steps after ester hydrolysis is loss of CO2. And so that type of reaction is called a decarboxylation. Decarboxylation is defined as loss of CO2. And other than loss of CO2 and breaking that carbon-carbon bond, everything else is the same. The methyl ketone's still there, and this carbon's still there. Good, so in the next one, we have another special case of a reaction that's neither an oxidation nor a reduction. The reason is that this carbon gets oxidized because we get a new bond from that carbon to oxygen, but this carbon gets reduced because we go from CH to CH2. So this type of reaction is neither an oxidation nor a reduction. And I think you'll agree that we've added an H to this carbon and an OH to that carbon. H plus OH makes H2O. And so this is an example of a hydration reaction. But we have two types of hydration reactions. We have electrophilic hydration, and we have conjugate hydration or Michael hydration. And the way we defined them in class, we said that conjugate hydration occurs when the carbon-carbon double bond is conjugated to a carbonyl, to C double bond O. Then it's conjugate hydration. When that carbon-carbon double bond is not conjugated to C double bond O, then it's an electrophilic hydration. And that's the case over here. I really should have made this a wedge or a dot bond, but too late now. I'll change it as I go, because that's a chiral carbon. So I should pick whether it's a wedge bond or a dot bond. Good. So this is an example of an electrophilic hydration, because we've added H2O to a double bond that is not conjugated to a carbonyl. In the next question, everything stays the same except carbon 1. And carbon 1 goes from a primary alcohol to an aldehyde. And maybe if I redrew the compound like this, it might be a little bit easier to see what's going on, because you can see we're going from C single bond O to C double bond O. And we're also going from CH2 to CH. So in the end, we have more bonds to an electronegative element and fewer bonds to hydrogen. Both of those are definition of an oxidation. And I would expect that you would recognize going from a primary alcohol to an aldehyde as an oxidation reaction. And I'll just make sure that I'm matching the answer key: reduction, isomerization, decarboxylation, electrophilic hydration, oxidation. Good. That leaves us with the next 5 problems. In the first problem, we have 2 esters coming together to make a beta keto ester. And it's worthwhile to recognize a beta keto ester as the product of a Claisen condensation reaction. We covered that in chapter 23. So beta keto esters are typically the products of a Claisen condensation reaction. And the reaction goes by, let's see, connecting this carbon that carbon is going to get deprotonated by base and make an enolate, and then that enolate will attack this carbonyl carbon. And it will go through the exact same mechanism that we went over in chapter 23. We'll lose a molecule of methanol, and we'll make this beta ketoester. So this is an example of a Claisen condensation. And Claisen condensations also occur in biochemical systems. All right, so the next question has CH2OH going to CH2O phosphate. And that falls under the definition that we gave in class of phosphorylation. We're doing essentially the alcoholysis of an anhydride. And we went over what that mechanism looks like in class. It's exactly the same as alcoholysis of an anhydride, which we covered in chapter 21. So whenever you see OH going to O-phosphate, that's a phosphorylation. And I suppose it's possible to phosphorylate a nitrogen too. I've just never seen it happen. I've only ever seen it happen on an oxygen. Good. And on the next one, we're adding part of the molecule. We're adding these three atoms. And you can see that we've added CO2. And that's the opposite of a decarboxylation reaction. That's a carboxylation reaction. And we covered that type of reaction in chapter 20, I believe, when we talked about the carboxylation of Grignard reagents, when we talked about making carboxylic acids by treating a Grignard reagent with carbon dioxide. So we talked about that reaction and its mechanism in chapter 20, but that would be an example of a carboxylation reaction. In the next reaction, we're again going from a carbon-carbon double bond to a carbon-carbon single bond. And one of the carbons is getting OH attached to it, and the other one is getting H attached to it. So we're adding HOH, or H2O, once again. This is a hydration reaction. Loss of water would be a dehydration. Gain of water is a hydration reaction. We talked about reactions of that type in chapter 7 and elsewhere. Now, the only question is which type of hydration? Is it an electrophilic hydration or a conjugate hydration? And in this case, the carbon-carbon double bond is conjugated to a carbonyl. So that means that it's a conjugate hydration or a Michael hydration. Both terms are equally correct. Both terms are equally acceptable. You could be given either, or you could use either. They're both acceptable. And then, last but not least, we have a ketone and an aldehyde coming together to make a new compound, one new compound that has a new carbon-carbon double bond in it. And that should be a familiar reaction from chapter 23. That is an aldol condensation reaction. And in this case, what winds up happening is we deprotonate alpha to the ketone carbonyl. We pull off one of these two hydrogens, really one of these four hydrogens. There are four of them. And you make the enolate. The way you know that we pull off the proton here is because this compound, benzaldehyde, has no alpha protons. So you cannot make an enolate of benzaldehyde. You must make the enolate of the cyclopentanone and then add that into the benzaldehyde using the mechanism that we talked about in chapter 23. You would get at first the aldol addition product, which looks like this. Wait a minute, that's not right. The OH is over here. That's the addition product that you get initially. And then loss of water happens by an E1CB mechanism that we went over in class. And you get a new carbon-carbon double bond conjugated to the carbonyl. So these two molecules add, and at first you get this beta hydroxy ketone, and then this dehydrates. I don't even think you need to heat it in this case because the double bond is conjugated not only to the carbonyl, but also to a benzene ring. And in this case, I don't think you could prevent it from dehydrating even if you wanted to. So heat is not necessary. It would certainly dehydrate if you heat it, but I don't even think heat is necessary in this case. Not when you're conjugating the double bond to a benzene ring. So let's again double check my answers. Claisen condensation, phosphorylation, carboxylation, conjugate hydration, and aldol condensation. Good. So that's basically it for the chapter 29 practice questions. Let's move on to the chapter 31 practice questions. Main thing we focused on in chapter 31 is drawing structures of polymers, both of addition polymers and of condensation polymers. So the question says, draw the polymer that you get from the given monomers. And that's all you need in terms of information, is to be given the monomers. You don't need any other information. The first four questions have only one monomer. So those are going to be addition polymers that we get. They're going to be alkene polymers that we get from treating the alkene with probably a radical initiator. And remember our step-by-step method that we learned from for writing addition polymers. You first redraw the molecule, changing that central carbon bond by reducing the bond order by one. If it's an alkene, then make the double bond into a single bond. If it's an alkyne, then make the triple bond into a double bond. And then just copy whatever is on the carbons. We've got a benzene ring over here. And this is not the only correct way to draw this. I also just realized I got ahead of myself. I can't make it right, just C over there. I'll have to do this. So I've redrawn that monomer with making the double bond into a single bond. Next, surround your compound with parentheses. Like this. Next, extend bonds through the parentheses to the left and to the right so that those two carbon atoms obey the octet rule. And then finally, add N to the lower right of the right parenthesis to show that everything inside the parentheses repeats an arbitrarily large number of times. And yes, you can write CH2 instead of drawing out the CH bonds. You can also put the CH2 before the carbon with the benzene ring. There are a variety of other ways to draw this compound that are equally correct, equally acceptable. And we went over all of them in class. We went over all of those different possibilities. But that would be one correct way of drawing the polymer, which is polystyrene. And of course, you don't have to draw out the benzene ring. You can just write pH if you want to. In fact, I'm going to do that so that I have a little more room. We'll do the same thing now with this structure. First, draw out the compound you're given. There will be 3 H's. And 1 carboxylic acid group. Like that. Next, surround your drawing with parentheses. Next, extend bonds from those carbons through the parentheses so that the carbons obey the octet rule. And finally, add N to the lower right. The next one, same thing. We'll even do this one a little differently. So first thing we'll do is turn the double bond into a single bond. Then we'll surround our structure with parentheses as best we can. Something like that. Then we will extend bonds from these carbons through the parentheses so that these carbons obey the octet rule. And then we will add N. That would be an acceptable way of drawing the structure. If you're uncomfortable doing it that way, then just keep doing it this way. I'll show you what it looks like doing it the other way. No, I'll copy this one. Either way is fine. Both are perfectly acceptable. And last but not least, we have an alkyne as the monomer. That is certainly allowed and something you may encounter on the exam. What we do is we turn the triple bond into a double bond. Remember, reduce the bond order by 1. And then just copy everything else you see there. We've got an ethyl group. We've got a hydrogen. Next, put parentheses. Next, extend bonds through the parentheses to make sure our carbons still obey the octet rule. And then put N to the lower right of the right parenthesis. Looks a little ugly, but I did the best I can. It's certainly perfectly acceptable. Follows all the same rules that we had in class. We just followed the exact same step-by-step method. In both cases, whether your compound is an alkene or an alkyne, the first thing you do is reduce the bond order between the 2 central carbons by 1. And the way to find the atoms that you do that to is by looking for a carbon-carbon multiple bond. So you leave alone all carbon-nitrogen, all carbon-oxygen multiple bonds. You leave them alone. You only go after carbon-carbon bonds. And of course, you're not going to disrupt the aromaticity of a benzene ring. You won't go after one of these double bonds. You'll go after the alkene double bond and leave the benzene ring alone. Likewise, we left alone the carbon-oxygen double bond and went after the carbon-carbon double bond instead. And same thing here, we went after the carbon-carbon triple bond and turned that into a double bond. And so the polyalkyne structure would look something like this. Maybe if I tilted those parentheses a little more, it might look a little better. Let's see if I can manage. Maybe something like that. That looks a little better. Either way is fine. So that's how you draw the structures of alkene and alkyne addition products. Next, we come to some polyamides. And the way I know it's a polyamide is from the starting materials I'm given. I'm given a diamine and a diacid chloride. And remember the rules we said in class today. We said that you start by taking off an H from each of the ends. So that's going to go from NH2 to NH. And you also remove the Cl's from the acid chlorides and connect the N's to the C's. You make new CN bonds. You make amide functional groups. So there we've just changed NH2 to NH. I think I'm going to have to do something like this to make ChemDraw happy. We'll just make a new CN bond over here, like that. And we'll extend that carbonyl group's bond through the parentheses. Oops, we want double parentheses. Like this. Oh, I just noticed that. You can enter a label right there. That's interesting that it automatically knows. So that's the answer to problem 5. Let me check my answers to make sure that we're okay so far. Yes, that's equivalent, that's equivalent, that's equivalent, that's an equivalent answer. And this is certainly an equivalent answer to that. And as I said today in class, this is not the only correct way to do it. You could put the carbonyl portion first. Connect that carbon to the nitrogen and make an amide. And connect that carbonyl to the end of the polymer chain. There we go. It adds the N automatically. So that's another correct way of doing it. Either of these choices are equally acceptable and equally correct. And of course, there's an infinite variety of little different changes you can make in the structure that would also be acceptable. We've known that since the beginning of Organic 1, that there are an infinite variety of ways to draw a structure correctly. There's any number of little changes. The carbonyls could point down instead of up, for instance. That's not going to make any difference. I expect after 2 semesters of organic chemistry that you're confident enough in structure drawing to understand that and to know that there's multiple correct ways to draw any given compound. Now, as for the next one, we will follow the same exact procedure. We change NH2 to NH. And we remove the chlorines from the acid chlorides. Then we connect the nitrogen to one of the carbonyl carbons. I could find fault with that bond angle. It really looks a bit ugly. That's about 10% better. It's still a little ugly, but correct. Absolutely correct. Both were absolutely correct. And then we surround with parentheses so that the bonds go through the parentheses and put N at the lower right. So that would be one correct way of drawing the polyamide, the nylon structure that you get. Let me see how I did it in the answer key. It's the same thing, same connectivity. Everything's connected exactly the same way. So that's how you draw a polyamide. Whoops, I don't want the answers. I want the questions. Let's do the polyesters next. The way I know it's a polyester is because I'm treating a diol with a diacid chloride. And just like treating an alcohol with an acid chloride, that's alcoholysis of an acid chloride, you'll get an ester. If you treat a diol with a diacid chloride, you'll get a polyester. And we use the same rules as before. We remove the H's from the O's. There's going to be bonds coming off of them instead. And we remove the chlorines from the diacid chloride. So let's bring this carbonyl group. I can't prevent it from writing those H's in, but we'll bring the carbonyl group in proximity to that oxygen and draw a bond from the oxygen to the carbonyl to make an ester group. And with that, we've included all of the monomer atoms that make it into the product. The way we know we've got all of them is that there's nothing repeated. You've got OCH2CH2O happening once, and you've got carbonyl, cyclopentyl carbonyl happening once. All you need to do is add N, and you do need to remember the N. All you need to do is add N, and your polymer is done. So that's one way of doing it. You could also have put the 2 carbonyls with the cyclopentyl group in it, the cyclopentane between them first, and then OCH2CH2O, and then put your parentheses. Perfectly fine. Equally correct, equally acceptable. And next we have a different alcohol and acid chloride. So we'll start by removing the hydrogens from the OH groups. I might try to draw this slightly differently just so it looks a little more linear. You don't have to, it's optional. But I think it will look a little better. And then we will, of course, remove the chlorine from this acid chloride. So we basically need 4 CH2s. I'm probably putting a lot more effort into this than I really need to. And I don't even need to put the letter C in there. It's completely fine without it. Then you surround it with parentheses and N. So here I've done the diol portion. I've made my ester functional group that makes it a polyester. Then we go through 4 CH2s to the next carbonyl, which gets attached to an O of a diol. We've already got that included in our structure. So that's another example of a polyester. Let's see how we did. Yes, that's the same. And that's the same. Good. The next two are going to be polycarbonates. In which we react phosgene with a diol. And as we said in class, you start by taking the H's off of the OH's and the Cl's off of the phosgene. And then just connect the carbonyl carbon to one of the oxygens to make an ester. And that should be all you need to do. So that's an example of a polycarbonate. What makes it a carbonate is O, C double bond O, O. That's the definition of a carbonate functional group. And the next one will do the exact same thing. We take the Cl's off of the phosgene. We take the H's off of the OH groups. We bring the oxygen of one of the OHs in proximity to the carbon to make a new carbon-oxygen bond to make an ester. And that contains all of the atoms of both monomers that make it into the final polymer structure. And then you surround it with parentheses and N. And I could have drawn the diol portion first and then C double bond O in the parentheses. As long as you have only one C double bond O in your polycarbonate structure, you're fine. Polycarbonates should have exactly one C double bond O carbonyl in their structure. Let's again see how we did. That looks the same, and that looks the same. Made them a little prettier in the answer key. Last but not least, let's practice our polyurethanes. Urethanes are the same thing as carbamates. And we defined the carbamate functional group. Oh, wait, I've just put the answers. I don't want the answers. I want the questions. But there's a couple different ways of making carbamates. One we discussed in chapter 26 by taking an amine and an anhydride, a special kind of anhydride like Bach anhydride, Bach2O, as Active calls it. And the other way is by addition of an alcohol to an isocyanate. And if you take a diisocyanate and a diol, then you will get a polyurethane. And so what you need to do first, if you'll recall, is change N double bond C to NH single bond C. The C double bond O stays the same. And you do that on both sides. You change N double bond C to NH single bond C. And the C double bond O remains the same. So you get a structure something like this. Don't forget to extend your bonds out so that carbon continues to obey the octet rule. We also take the H's off of the O's in the diol, and then we just move one of those H's into the proximity of one of the carbonyls and make a bond. And now you have all of the monomer atoms that make it into the polymer. Surround what you have with parentheses and N, and you are done. And I could also have put O, CH2, CH2O, and then this dicarbonyl portion. There's an infinite variety of other correct ways to write it. Your H doesn't have to go above the N. It could be below the N. You could draw out the NH bond if you wanted to. There's infinite variations on these that are also correct. And then for our last one, we'll do exactly the same thing. Remember that you change N double bond C to NH single bond C. And leave the C double bond O alone. Do that on both sides. Oops. And then you remove the H's from the O's in the diol. Those H's actually wind up on the nitrogens. That's where you get NH from. And then bring one of those oxygens near to one of the carbonyls and make a bond so that you complete the carbamate or urethane functional group as we defined it today in class. After that, add parentheses and N, and you are done. That's how to draw the structure of a polyurethane. Double checking. Yup, looks good to me. Pretty much the same. Good. So that covers at least the majority of what you'll need to know from chapters 29 and 31. They're the main things that we covered in chapter 29 and 31. So as usual in organic chemistry, we're focusing on structure. And that's basically it. So I knew this would be a short review session. Where'd my cat go? My cat's not here to say goodbye. Oh, there he is. He's way in the back of the room. Can you see him on the camera? Yes, actually you can. He's right here in the corner. He's keeping a close eye on us. So good. Hopefully that was helpful. If you want more advice on drawing polymer structures, feel free to bring whatever you're drawing to my office hours. I'm happy to help. Also, if you need to go over mechanisms and want to make sure you're drawing them right, feel free to stop by my office hours. That's what I'm there for. So this video should go up the same day. It takes a little while for Zoom to finish. What's the word I'm looking for? To finish making the video, let's say. So once the video is produced on Zoom, I'll download it and then I'll upload it to YouTube. So I wish you all the very best on the final exam. It's been a pleasure to instruct you this term, and I just wish you all the best. I wish all the best for all of you. I will see you all in the final exam.